Hi everyone. Today I'm going to give you a brief about the major project for the manufacturing of the power auto gear pump. So first I have to remind you that this is not going to be a just lab report. It's going to be something what we call the manufacturing report for the gear pump. First thing we are going to start with is what is the thing we are looking at. Now we have two pumps in the lab. The first one was the gray one, which is half gutted, to show you all the dimensions and show you all the details what we have inside the core of the pump. This one is the PUK S850R. Well, the pink one, where we have all the shafts, the long one, and the same one I sent you the drawings for it, is actually the PUK S85R, and you can read that on the plates on the main body. Now the only difference between both is the size, and bigger size, actually the pink one is going to pump more hydraulic per minute. So it's actually going to have the Q value, which is the pumping of the liquid, it's going to be 85 liters per minute. So what we are going to have different between the pink and the gray is that the pink is going to pump more fluid. That means it's going to require more mechanical power, and of course going to generate more hydraulic power. The torque is going to be higher, and we are going to go through these things within the slide. The sizes, because the pink is bigger, so the shaft is going to be bigger, the diameters is going to be different. So the question was, what are the materials of the main components? You have to state what the material you are using at the beginning of the report. Actually, at the beginning of the report, we are going to come to the main 5 pages we had in the report paper. But if I can talk about the materials, and that's what we are going to order in the section of the materials. So for the external, we are going to need some casting material, because it's casted material. So for the external, like the head and the bracket and the casing, we are going to order either the iron or the SG iron, the steel, high alloys, or composites. Now we mentioned earlier in the casting lecture that you usually going to go for the lower melting temperature. Having the steel or high alloys or composites, that means we are going to need higher melting temperature, sand casting in all the cases, but this means we are going to need more energy, and this will make the cost of this pump quite expensive. So the one we having, actually the model we're looking at, is going to use the SG iron, the sand casting iron with sand gray casting iron, SG iron. For the internals, like the shafts, we are going to use the steel. No need to use the high alloys. Usually when we are going to have high alloys, that means we are going to have very high temperature in the working. That means this pump is going to work under very high temperature, so we will need to have high alloys in the manufacturing. So the material is going to be, for the external, is SG iron. For the internal is going to be steel. For the internals, the gears, which are actually part of the shaft, is going to be steel as well. For the pushing, we are going to use the Teflon coated steel bushings. Why Teflon coated? Because this will absorb some of the hydraulic during the operation and keep it to prevent the dry starting process. The shaft seals, like the packing and the lip seals, actually these are off-shelf item. We have the thrust plates. The thrust plates are made from aluminium, and we're going to talk about the manufacturing process of this one soon. Set of bolts are required, and of course we said we have some washers and seals. So when you make the orders for the material, you can make a table. You will say, okay, I need an SG iron. The quantity is going to be just hash because we don't know the number. This is just a training on how to write down a manufacturing report. For the internals, once again, steel is going to be in the shape of the bars, and the dimensions of these bars are going to depend on what is the dimensions of the maximum diameter you have on the shaft you choose. For the one we had for the model PUK 85R, the maximum diameter on the gear was something about 57 to 58 millimeters. That means if we are going to go to the standards of the bars, we are going to use something about 60 millimeter diameter bar. The length of the shaft is going to be something about 210 millimeters, after the facing is going to go down to 204 millimeters, as you can see in the engineering drawings. But in all the cases, once again, we're not going to mention any quantity. We're only going to say steel bars, and you can say what the grade of the steel, and the quantity is going to be hash once again. For the pushing, you can put a quantity by number, because actually you have to use 4 pushes for each pump. So you give the dimensions, that means the internal diameter, the outer diameter for the walls, and what's the length of the pushes. You have to write down it should be Teflon coated, and definitely this is very advanced manufacturing process, so you're not going to make it in the same factory you are going to make these pumps in. The shaft seals, the backing and the lip seals, which are made of rubber or combination of rubber and aluminium, actually these are off-shelf items, you don't have to manufacture it. The bolts and nuts are off-shelf items, you don't have to manufacture it. For the thruster plates are made of aluminium, so you are going to require a quantity of aluminium, unknown quantity of aluminium. Going to the next stage, what are the material of the thruster plate and why this material is chosen? So we say it's made of aluminium because the aluminium is more ductile than the steel, more soft material than the steel. So while the shafts are going to turn, the friction between the gears and the walls are going to be prevented, because we are going to have friction between the gears and the thruster plates. The thruster plate have some grooving system, and this grooving system is going to maintain the pressure inside the gear, in the gear cavity, in the flow cavity. Okay, so they designed on purpose. How they are made? Aluminium need to be made by the die casting, because the shape is not that complicated. So die casting, we have to make the die injected with the aluminium. We can either use the hot chamber or the cold chamber die casting process. We don't have to mention these details, we're only going to say it's going to be done by the die casting. Why does the pump have to be manufactured to such close tolerances? The most important thing is we have pressure inside the pump. If we are going to have loose or tight for the parts, then we are going to lose power, because we have to start it in very tight tolerances. If we are going to have large tolerances, we are going to generate vibration, and this vibration can cause the explosion for the pump due to the resonance. So very high velocity, the tolerances should be 2 close values, and this will make it perfect contact between the surfaces, so no wear, no vibration, no loss in the pressure. Which dimensional in the tolerances are critical? Well, actually every contact parts are going to be high tolerances area. So we're talking about the contact gears, we're talking about the shaft and the bushes and the cavities we have inside the main body. The dowels, because the dowels are going to be in fitted press, so the hole actually should be drilled and then going to be reamed to have a very high tolerance dimensions. Now, how the bearings are lubricated, we mentioned that because they are Teflon coated, so the Teflon is going to absorb some of the hydraulic, and this will prevent the process of the dry starting for the gear after a long period of ideal state. So for the pump, on any catalog we will find this chart. This chart, it will have the PWO, which is the pump series. 0 is the rotation. 0 is mean opposite to the engine, or the S is going to be same as the engine. How we can do this one? By having a gearbox to make the direction of the rotation opposite or the same. The 90 is how much flow rate in liter per minute we are going to have per 1000 RPM for the shaft. So this number is 90. We can see there's a chart here. In this chart we cannot find the 85, but actually the 85, that means we are going to have 85 liters per minute. So for this one you can see that the table is, if we are going to have the CS 25, that means it's pumping 23 liters per minute. The 90 minute is going to pump 88 liters per minute, and so on. Always remember that the RPM is going to be 1000, and this will help us to do all the calculations. So to do the calculations, to find what the motor size in kilowatt we have to use to generate, to make this pump operate with the specified flow rate. So the equation we had is that the delta P, the power hydraulic is equal to delta P, which is the pressure difference between the inlet and the outlet port. Because you know that we are going to suck the hydraulic in low pressure and we are going to pump it at higher pressure. The higher pressure minus the lower pressure is going to be the delta P. Usually we are going to take this figure as 310 megapascal. You know that the unit of the pressure is Pascal, which is in Newton over meter square. The Q, which is the flow rate, is in cubic meter per second. Now you saw that the value we had in liter per minute. You have to remember, if you want to change it from a cubic meter, from liter per minute to cubic meter per second, you have to divide the value by 3600, because simply we have 3600 60 second per minute, and we have that in a cubic meter we are going to have 1000 liter. Then we are going to make the exchange and we are going to have the flow rate in cubic meter per second. Now why we have to get it in cubic meter per second? Because the unit for the power is going to be Pascal, we said, is going to be Newton over meter square, and the Newton itself is kilogram multiplied by meter over second square. That's make that the unit of the power is going to be kilogram cubic meter square divided by square meter multiplied by cubic second square. On the other side, we are going to have the Q is in cubic meter per second. So after simplification, we are going to have the unit of the joule per second, which is the power in watt, and then we can change it to kilowatt. For the P shaft, that's the P hydraulic. Now, usually the P hydraulic is the power supplied by the shaft, which is coming from the motor, multiplied by the efficiency of the motor. Because we are going to have some losses. These losses are caused because we are going to have compressibility of the fluid, again to have some fractions between the parts and so on. So the value of the efficiency you got for this project is something about 70%. I don't remember that. So to find you are going to find the P hydraulic, the power in hydraulic in kilowatt, then simply divide this value by the efficiency and you are going to find the value of the P shaft. Usually you have to get the power of the shaft is higher than the power of the hydraulic. Now this will be stage number 1. Then we go to the stage number 2. We have to find the torque value. Now we can see that we have an equation here said that the P shaft, the power of the shaft, is equal to the torque multiplied by omega. T is the torque in a Newton meter. Omega is the radial velocity, which is going to be in radius per second. How to find the value of the omega? Simply, you know that we have the RPM is equal to 1000 revolution per minute for this pump. Try to search for a formula to change the RPM into radius per second, RAD over S. When you get this value for 1000, you are going to use this equation. You know the P shaft value, you got the omega value, divide the power of the shaft by omega and you will find the value of the torque in Newton meter. Just remember that the power of the shaft should be in watt, not in kilowatt. Now, for the example of the gear shaft, now in one of the questions you have to sketch that, and then you have to make the number of the culture again to have the final diameters. Now just remember, this is an example of the gear shaft. These dimensions are not actual dimensions. Whatever the pump size you are going to use in the lab, 50 or 85, you're not going to get these dimensions. We're never going to have 77 millimeter diameter for the gear. For the gear of the PUK 85R, the diameter is not 77, it's going to be 57.5 or 58 millimeters. The length of the shaft total is going to be 204 millimeters. Actually, we are going to add something on the side to take it to 210. So if I get to have the maximum diameter is going to be 58 millimeters. That means that the nearest maximum, rounding up diameter I'm going to have for the shaft bar as the raw stock is going to be something about 60 millimeter. That means my first cut for the part number 1, if I get to the next one, okay, I have to take it from 58 to, from 60 to 58. That means my first rough cut is going to be something about 0.7 millimeters only. I'm going to take 0.7 millimeter cut just to take it from 60 millimeter to 58.5. Now, why I took it to 58.6? Why I have to take it to 58.6? Because I'm going to leave something about 0.3 millimeter from the radius to be removed by the finishing cut. This was rough cut. That's means I'm going to do it very fast, and then I'm going to have the first cut to be done. Now, to calculate the number of the cuts required to do the second stage, which is here 50 millimeters, the actual one is 32 millimeters. To have these dimensions, I can make an equation. It's a very simple equation. I'm going to subtract the bigger diameter, the original diameter, minus the final diameter. Okay, now for example, in this example I can see in front of me 77 millimeters minus 50 millimeters. We're going to have the difference in the diameter, which is going to be something about 27 millimeters. If I'm going to divide this one by 2 multiplied by the maximum depth of cut, or the depth of cut I'm going to use, let's say that the depth of cut is going to be 2 millimeters. So 27 divided by the 2 multiplied by 2, which is 4, I'm going to have the value of, just make the simple calculations, 28 divided by 4 is going to be 7. So actually I need to have 7 passes to cut from 77 to 50. The same thing I can do it on the other side. From 50 to 25, I have to do it something about 25 divided by 4, and I'm going to have 25 divided by 4 is 6.5, so I have to round it up to 7. So 7 passes need to be done to do the other cut. We have to do 2 operations because it's very hard to hold the part, and also you remember that we talked about the cutting tool itself. We have either left-handed or right-handed cutting tool. You cannot use the left-handed one. Left-handed means that the tip is going to be toward the left side. It's going to move from right to left. So we can do the operation number 1 by using this cutting tool. Again, to do the facing first. That means I'm going to insert the cutting tool in the face of the bar, and then I'm going to move it toward the center point and remove 1 layer from the face. That's what we call the facing and the turning operation. Then I'm going to move it toward the end to the red line by using the feed rate value, which is given as 0.4 meter per second or millimeter per second. Okay, and this will be called the turning process. I'm going to remove from the diameters, not from the length. Okay, doing multiple cuts, and then until I'm going to have the final cuts to be done. So the feed rate is given, the velocity is given for different cutting tool. Then I can calculate what the value of the RPM I would like to have. Finish all the cuts for the operation number 1. Then I have to turn the part and do the operation number 2. I said yesterday in the class that you can suggest to reduce the time of the unloading and loading of the part to the position number 2. we can use the twin spindle lathe machine. Just remember, you can suggest that, but you cannot force your company to have this machine, because this machine is being an investment. They have to pay something about $100,000. They're not going to spend this money for one product. So the operation number one, we have the cutting data for the high-speed steel insert is going to be 60 meters per minute, which is the velocity. The for the carbide insert is going to be 120 meters per minute, and for the ceramic turning insert is going to be 220 meters per minute. The maximum depth of cut is going to be 2 millimeters, and the feed rate for the roughing is going to be 0.4 millimeter per revolution, and the feed rate for the finishing approach is going to be 0.25 millimeter per revolution. Now you remember we said that for the case of the finish cutting, you can increase the speed, but you have to, for the rough cutting, increase the speed, reduce the speed, but increase the feed rate. In the case of the finishing, increase the speed, but you have to reduce the feed rate. The equation to be used to calculate the RPM value, we only have to multiply 325 multiplied by the V value in meter per minute divided by the D, which is the diameter of the part, the workpiece, in millimeter, and this will give you the value in RPM. The Excel sheet I gave you, well, actually it's been given to you. I designed this Excel sheet to calculate the diameter and using the same new diameter to calculate the new RPM. So that's why you can find that the RPM value is going to be increased rapidly. In the real life, we set the RPM once. We don't have a feedback value for the RPM to change the for the diameter to change the RPM value. For the studded face, we have to do the face milling process first to make a new fresh face. Now just remember, when we are going to make this one by using the sand casting, we are going to have very rough surface from all the sides. So the surface of this face actually is going to be something similar to the roughness of the sides of this block. And inside we have to put a core to have these holes. So we don't have to create holes by drilling. We're only going to have a rough holes, and we have to enlarge this one by using the boring process. Okay, now in the slides we talked about the multi-stage boring and facing for the bore process. Now once again, this is a custom design cutting tool. You can suggest to use it, but you cannot, once again, you cannot force them to buy it. If we are going to put this block on the lathe machine, on the milling machine, and we have to clamp it from the side by using a vise. Now just remember, we're not going to use the clamp device because we're doing a facing process. That means that the cutting tool should be passed through the face. If it's going to pass through the face, we cannot use the clamp which holding the part from the face itself. So we are going to use a vise device from the sides and hold it very tight. We start to do the first cut, which is the face milling, having a fresh surface which is going to be quite tolerant to the dimensions we had in our design. Then after the new surface has been created, I can do the internal boring for the cassette faces, boards. You know, you can get the diameter of this one because actually it's going to be 58 millimeters, the same diameter of the gear itself. Cut it to the same length of the gear, and then we are going to have internal facing for the bottom, and then we are going to have the internal boring and finishing for the internal places where we are going to have these pushes in. Now after do the boring, we enlarge the size of the hole. Then simply we can do the reaming process to provide a good surface finishing and tolerance for the internal bore. After we finish this process, now we have fresh surface. We are going to have two bore hold with very high quality surface and tolerances. Then the next stage is going to do the drilling on the milling machine itself. We don't have to take it to the drilling machine. Simply we are going to make a drilling from point to point to have these 6 threaded points. Drilling, then tapping. The drilling and the tapping can be done on the milling machine if we are going to have a turret device which is going to hold multiple cutting tools at the same time. In the case of the, I think that the diameter of this one is something about 10 millimeters, and the thread, I don't remember the standard for the thread. Anyway, for the stud holes where we're going to have the dowels in, now this one we said it should have very high tolerances. That means it should need to be drilled and then need to be reamed. The drilling is going to give you the rough diameter, but the reaming process is going to give you the exact diameter, which should be something a little bit smaller than the diameter of the pin you are going to insert in, which is known as the dowel. Now on the other face we are going to have once again face milling. Now you can see that we have some scratch on these ports. This scratch has been done by the face milling cutter. Later you can stamp these numbers, as you can see, number 1. So we do the face milling. We said we have a hole because we already put a core during the casting process. So of course we have to clean this one. Actually it should be cleaned earlier. Then we start to do the boring process. We just enlarge the diameter to a certain value. Then we are going to do the internal thread using the rotating cutting tool. It's not going to be a tapping, because this diameter is too big to be tapped. So instead of that, if you just search about doing the threads for big holes on the milling machine, you'll understand the operation I'm talking about. I'm going to send you another video than this one. It's going to give you some ideas about how to manufacture these things. So we can simply make another table. It can be an Excel sheet about the operation we're going to have. So we start with the solid faces. What are the operation and what will be the description? What will be the tool we're going to use? The insert, the manufacturer of the insert, and the cutting speed required, and any other comments if you have. Now these tables actually are not very hard to be filled. So the first operation, for example, is going to be the mill studded face, which is the face milling. The tool is going to be any cutter for the face milling cutting. Usually you have something now which have multiple teeth, multiple cutting tools on the milling machine using the carbide insert. Now if I'm going to use the carbide insert, that's what we are going to write here: multiple teeth face milling cutter in the tool. The insert is going to be carbide insert. Try to find anything online and put the insert number, for example, the manufacturer, any manufacturer. The cutting speed, we said that the cutting speed available for the carbide insert is 120 meter per minute. Any comments if available. Now we are going to do the same thing for the boring process. Try to find any boring cutter on the milling machine and fill the next operation, which is going to be operation number 2. The same thing for the drilling, the same thing for the tapping, the same thing for the other drilling for the dowel holes, and for the reaming process for both the bores and the small holes for the dowels. Now you need to write down a section about the material for the pump, as we said earlier. So as you can see here, we have cast iron to be used for the blocks. For the shaft is the steel bars, off-shelf items for the seals, and the aluminum for the thruster plate. Thruster plate, as I said earlier, is just 8 shape, I mean number 8 shape, with the holes in the middle which have something like 32 millimeter diameter. We have to provide the shape of the grooves we have there. You don't have to machine the grooves. You can do that by the die casting process. Now the bar stock, as we said yesterday in the in the lecture, that the diameter we can have for the bar stocks are starting from 5 millimeters, 10 millimeters, 15, 20, 25, 30. After 30 is going to increase by tens, so 30, 40, 50, 60, 70, 80, 90, 100. From 100 we are going to jump to 150, 200, 250, and so on. So the diameter you're going to use is something about 60 millimeters. If we are going to use the actual dimensions we have for the gear we have in the manufacturing process. Now cutting the supply is going to be done by the process of the broaching. So you know that the broaching is multiple teeth which have the taper shape. So the first teeth is going to be small, then it's going to increase until we're going to have the required shape. So that's why you can see that the shape of the supply at the end, close to the next bigger diameter, is going to be a circular shape. Now just remember, when you do the engineering drawing and your calculation, just ignore the taper shape for the between the supply and the shaft. Just consider this will be a straight shape. The cutting of the gear, well, this is something about how you are going to make your calculations. Usually if you are going to manufacture less than 100 parts, you have to do on the machines you already have. So if I'm going to do 100 parts, 1000, even 1000 parts, I don't have to buy a new machine to do the gear hopping. Simply I can do the cutting of the gear by using this cutting tool on the milling machine. That's what we call the gear teeth cutting tool on the milling machine. And then we are going to use something called the indexing plate, which is going to divide the circle into equal amount of divisions. It's not angles, actually it's divisions. And this will be decided about when we are going to decide what will be the number of the teeth required for our gear. This one is very simple gear because this one is straight gear. We have another thing which called the other gear. I forgot the name because I'm so tired today. Anyway, so basically we can do the cut on the milling machine, and if we're going to go for further complicated cut, we can do the cut on the other machine, which is more advanced, what we call it the milling turning machine, which are going to have 5 axes for the cuts. Or if I'm going to do this by mass production, we need to process something about 2000 shaft per week, for example, then we can buy a gear hopping machine. If you don't want to buy this machine and you cannot force your company to buy this machine, simply you can have a subcontractor to do the cut for you according to your dimensions. Now, we talked about the gear hopping, and we said that the most expensive thing we have is the cutting tool itself, because this one is custom made according to the dimension of the gear you are going to have. So we will go back to the first point, which is, okay, now we can simply get the cutting tool and do everything on the milling machine. Yeah, the other type of the gear, like the one we have on the turning milling machine, is called the helical shape of the gear. After we did all the cuts for the gears and the bar, we have to have a super finishing for it, because it's going to be rotated at very high velocity. So we have to prevent any friction. Well, actually we're not going to prevent it, we're going to limit the friction. So the best way to do that is have the grinding process. That's why the shaft we have in the lab have 2 holes from the end, because simply it has been supported, as you can see here, from centers on the, I'm talking about the shape on the left side. After you did all the grinding for the shaft, you can do the grinding for the gear teeth itself, because we said once again you should have very close tolerances to each other, and also we should limit the friction between the both sides. So the best thing to limit the friction is to have very good surface finishing by using the grinding process. So the shape on the right is during the grinding process for the gear teeth. Then we have to do the final inspection for the shaft. We have to check, I think you remember this device, we use this one in the metrology lab. So this one can do the checking what's surface roughness and what is the dimensions we have on the gear teeth and the shaft itself. Now, after we made all the parts, the first part to the right has been made by the sand casting. Then we have to do a machining process. The dowels has been made by cutting a bar and doing the surface finishing on the grinding. The pushes has been pre-ordered, we're not going to make it. The thruster plate, die casting process. The shaft gear has been cut from the bar to be a shaft and gears. Thruster plates, once again, all the seals are off-shelf item. The bushes, once again, for the cap, actually it has been sand casted once again. The bolts are actually off-shelf item, and all the other seals as well. So we have to assemble all the parts we made to make it an assembly. This assembly to be tested. Now, how to inspect the assembled pump? 2 days ago, I sent you an email about the Australian standard for inspecting the pumps. This is a general standard. You can use this standard to check any pump for inspection of the duties. So the first thing we are going to do is just simply pressurize the case without the gears. We are going to close the sides or the inlet and the outlets, and then we are going to pressurize it with water. Now, why using the water, not hydraulic? First, because it's safe, it don't have any chemical reaction. Second, it's just water. Third, it can be compressed to a very high pressure. Now we are going to compress this one to check the leakage area, and also we are going to check how much pressure it can take before it's going to explode. Now, when I said explode, because actually that's happened. Usually the pressurized parts tend to explode, and this is very dangerous. So, for example, if this pump has been designed to take the pressure of 310 bar or 310 megapascal, simply we have to pressurize it to at least 10% more than the maximum value it's designed for. We keep it for about 5 hours under higher pressure, then we can release the pressure, and this is test for the pressure of the case. We can do the impact test. That's mean very simple. If I again to hit it with a hammer, and this will give us what will be the impact resistance for the case. That's for the case. Now we put the assembly of the parts together. We fill with the hydraulic through a circle. It's just only going to suck the oil from one side and pump it to the other side. Then we're going to start run it to a maximum velocity, a maximum RPM value, and keep it running for something about 10 or 20 hours. Now, if you remember, if you visit IKEA one day, you can see that they have a chair there, and they just simulate that people sitting on it multiple times, and they checked, okay, now how many times and what will be the span life of this chair. This is something about the failure test. We call it the failure test in engineering. So you are going to run the pump at very high velocity, and you are going to check what will be the life of this pump under maximum velocity. This is one of the tests also can be done. Now, for the sheet you have to answer these questions. So sheet number 1 actually is going to be about the introduction of your report. What the model pump you are looking at, what it's used for, what the material of the main components. You don't have to put the material of the main component within this within the introduction. Which direction does the drive gear rotate? What is the path of the oil? You have to sketch that. What is the material of the thruster plate and why this material is chosen? Why is one part is larger than the other? Which one is the suction port? Why does the pump have to be manufactured to such close tolerance? Which dimensional tolerances are critical? You have to, his sketch to be submitted. How are the bearings lubricated? What are the dowels used for? And for choosing pump, you have to do these calculations. Now, you have to remember that for this calculation, you have to change the number. The Q value is not 29. This is an example. The value you have for the Q is either 50 liter per minute in the case of the BUK SR 50R, or is going to be 85 liter per minute for the PUK S85R. The pressure is we are going to use the same pressure, and we are going to convert the unit as we saw in the example. Assume the efficiency is 70%. Calculate the shaft power. You are going to calculate the drive torque. Well, he said here that if necessary, ask your lecturer for assistance. So you asked me yesterday and I answer you now. Go to the page number 2. You have to do the material wastage when the machining of the driver gear. Now, just remember this carefully. We're talking about machining the driver gear. That's mean again, not driver shaft. So we have to do the whole calculations. That means we are going to start with the bar and we are going to finish with the cutted driver gear, the shaft with the gears and the supplying. Now, whatever you're going to read here, I'm going to give you a very easy process to do that. He said here, measure the driver gear, the supplying shaft, and produce a dimensional sketch. I send you the dimensional sketch. Determine the volume of the metal in the gear by displacement of the water in a measuring cylinder. We don't have to do that. Select available bar, assuming that the cylinder blanks are precision band sewed from the AIS, which is the American Iron and Steel Institute, of a grade 4340H bar stock, allowing for the surface wastage and end losses, and determine with suitable blank diameter and length. Calculate the blank volume, calculate the material wastage as a percentage of the material supplied, and as a percentage of the finished product. Now, let's start with the steps one by one. The dimension we are going to have for the model 85R are: the shaft total length is 204 millimeters. The maximum diameter we have is at the gear section and is going to be something about 58 millimeters. That's mean we are going to assume that the maximum length of the row bar was something about 210 millimeters. We are going to remove during the operation 3 millimeters from each face to get the dimensions of 204 millimeters. For the diameter, okay, now the 210 is the height of the cylinder, the height of the bar. The diameter we are going to have for the bar is 60 millimeters. Because we said it's 58 millimeters, we removed 1 millimeter from each side, therefore got 1 millimeter to have the 58 millimeter diameter for the gear. So we have the diameter of the base, 60 millimeters. The height of the cylinder is 210 millimeters. Change everything to meter. Then find the volume of the cylinder. When you get the volume of this cylinder, you search online about what is the density of the steel with the grade of 4340H. You will find something about 7,800 kilogram per cubic meter. You simply multiply the volume by the density, you will get the mass of the original bar. Okay, now to repeat this one once again, we calculated the volume of the bar stock. It was the area of the base, which is 60 millimeter diameter. 60 millimeter diameter divided by 1000 divided by square divided by 4 multiplied by pi. This is the area multiplied by the height, which is 0.21 meters. You will get the volume. You will get the small value because actually it's too small compared to the cubic meters. Now we got the volume multiplied by the density, which is 7,800 plus minus. I don't remember the figure specifically. You will get the mass of the bar before machining. Now, how to get the mass? Okay, now this is not weight, this is mass. How to get the mass of the machine part? Now this is not very hard task because we actually have the machine part, the shaft gear. If I'm going to put this one on scale, we'll get that the figure is going to be 1,557 grams, which means it's going to be 1.557 kilograms. Now we got the volumes, we got the masses. Now how to find what is the material wastage? How much kilogram have been lost during the machining process? Simply subtract the bigger mass minus the lower mass. I mean the mass of the pre-machined part minus the shaft which is machined. And we are going to get something about 2 point something kilograms. This will be the wasted material. To find what the percentage of the wasted material as a percentage of the material supplied, simply you are going to divide the wasted material value by the original mass value. This will give you a good percentage. Now, as a percentage of the finished product, that means we are going to simply divide the difference, which is the value of the wasted material, by the mass of the finished part. You can make a sketch. It's going to be simply a rectangular shape. In the middle, you are going to sketch the diameters of the bar, which is going to look like a rectangular shapes. You are going to hash the remaining part, which is the shaft blocks. From the outside, you are going to sketch lines which represent the number of the passes you are going to have to do the cut. Now, machining the driver gear, okay, it's required to sketch a blank envelope and show. Well, actually, we did that earlier, so you don't have to do that. Once again, describe the indicate of each lathe operation step on the shaft, showing the number of the cuts required, assuming that rougher cut to be well, it's 2 millimeters. You don't have to care about this one, and 0.2 millimeter for the finishing. Types of the cut: rough, finishing, parting, extra. Depth of each cut, the cutting speed. We talked about the cutting speed, and the indicated number of the steps required. Describe any rechucking considering necessary. Now, of course, we have to do the chucking number 1 for the face number 1. Then we have to turn it and do rechucking once again. Use references such as the Cabaglan and other books. You don't have to do that. Anyway, so the Excel sheet I supplied to you, you can simply use it carefully because it contains the same equation. And this actually going to give you numbers of the cuts you are going to have. Simply, I told you can do the same calculation by find the difference of the diameters divided by 2 multiplied by the depth of cut you are going to use. And this will give you the number of the passes from one stage to another. The same thing to be done when you are going to do the machining process for the block, which is the main valve body. Now we said we have to clamp it. Now he says here, consider that all the operations necessary for the machine and the finishing of the pump body, these should be discussed in the production context are to be necessarily restricted to automatic machine tools. So the pump body must be clamped and supported during this operation. Sketch and describe possible fixture or fixtures for the use on all the machining operations. Now, simply we are going to use the vise. We're not going to use any clamp because once again, when we talk about the clamp, that means we are going to use a device which holds the part from the top. We're going to do a face milling, so we're not going to use any clamp in this case. The machining process, we are going to talk about, describe each step in the machining process. We talked about this one when we saw the parts. Comments of any accuracy required. Actually, you don't have to do this one by description. You can have this table, you fill these tables. Okay, but at the beginning, you are going to talk about what the machines you are going to use. I'm going to make this one a different section, but first I get to go to the next one. So here in the report said, okay, now you are required to submit a full report on the processes used manufactured for the pump. The report is cover the 4 weeks of the investigations and advice from your tutors. It should include description of the pump, how it's work, and where it's used and extra. So this will be an introduction. Discussion about the material wastage of the gear, driver gear, as we did the calculation 2 pages ago. An outline of the manufacturing operation that you have decide upon during the project sessions. Discussion of the workflow of the materials through the possible factory. The report should be something between 8 and 10 pages long. The format should meet the school requirements for the professional report and must contain a summary and discussion of the main outcomes of your investigation. Drawing, diagram, table, charts also should be used where possible. Now, to give you a hint, many of you think, okay, now if I'm going to have 2 pages of drawings and I'm going to have another 3 pages for the sketches and flow chart, am I going to be limited to write just 5 pages? Now, the answer is no. You can write once again 10 pages of the report. This will not include the cover page. This will not include the page where you are going to have your name on it with all the fancy shapes you are going to add. And it's not going to include the drawings and the sketch and the tables you are going to add. Try to put everything as appendices at the end. Appendix number 1, you are going to refer to appendix number 1 in your text. So we can check your appendix number 1 and we're going to see there, for example, is going to be the engineering drawings. Appendix number 2 is going to be about the calculation of the cutting. Appendix number 3 is going to be the graph and the calculations for the wasted material calculations, and so on. So just remember, you have something called appendix, and you can put appendixes up to another 10 pages. So totally we are going to have 20 pages, but we are not going to be mixed together. If you are going to write down this one as appendix 1 to Z, for example, it's going to be an extra page. It's not going to be calculated within the 10 pages you have to write down in your report.